Good afternoon, everyone. I'm Aneri, and today I'm going to talk about my course project where I perform spatial analysis of the shrinking of Detroit through an agent based model. While the world's total urban population continues to grow, some cities are actually shrinking. This shrinkage has caused economic depression and contraction of housing markets in these cities. Such issues challenge urban sustainability with declining populations and changes in land use. Cities that heavily focus only on one industry for the economy are often not regarded as sustainable, as they are vulnerable to the decline of a single industry, causing a spike in unemployment rates, as was the case for Detroit and its reliance on the manufacturing industry. Residents of such cities have a higher chance of leaving to find other employment opportunities. Such employment mobility results in a large amount of vacant real estate in shrinking cities. Deindustrialization and the loss of manufacturing, construction, and retail has accounted for 60% of job losses in the 100 largest United States metro areas over the last few decades. Significant amount of vacant land and abandoned properties across an entire urban area is one of the key characteristics of a shrinking city. The unoccupied space results in higher rates of crime while being a detriment to the local economy and housing market. Due to the vacant properties, local governments collect lesser property tax revenue, resulting in lesser money allocated towards public safety and infrastructure, which in turn accelerates the population decline, thus causing a decline in real estate prices. This forms a negative feedback loop. This causes the local housing market to collapse completely in extreme circumstances. The city of Detroit is the largest city in Michigan, located in the Great Lakes area of the United States, which has also been given the moniker the Rust Belt region. There are many stories that discuss the greatness of this city during the 1950s, when the automobile manufacturing sector rapidly expanded and its population reached its peak. However, over the last 60 years, Detroit has declined and shrunk. The key reason for bankruptcy of Detroit was the increasing competition in the automobile manufacturing industry because of globalization. Detroit also witnessed a population loss of over 60% in the last 60 years and 25% in the 10 years up to the 2010 census. That accelerated the contraction of the housing market as manufacturing industry employees become unemployed and sought employment elsewhere. There were approximately 60,000 vacant parcels of land and about 78,000 vacant structures, of which 38,000 were considered to be unlivable in 2014 due to the potential for structural collapse. In this project, the shrinking of Detroit City after 2010 is studied on a micro level. The analysis is performed using a dynamic agent based modeling approach. A dynamic agent based model is used to simulate and analyze a shrinking city's housing market from micro level interactions, individuals' preferences, and trading interactions. The model allows us to explore how urban shrinkage emerges at the macro level through the simulation of housing trades at the individual level. The model uses decennial census data. Capturing housing markets is essential for understanding urban shrinkage, as the contraction of housing markets is caused by population loss under an urban shrinking situation. Agent based computational modeling is an approach to modeling complex social dynamics. In an agent based model, actors in a system are represented as autonomous individuals, households in the context of this project, in a computer program. Their behavior is governed by rules, including adaptation and interaction with each other and with the environment through time, and a starting configuration. The agent based model then simulates both individual trajectories and population level patterns or outcomes, which are generated from the bottom up by the decentralized actions and interactions of the agents. Such a model provides mechanistic mapping from individual level assumptions to co evolving population level dynamics. Assumptions can be informed by data or theory, and outcomes at both the individual and population levels can be compared with data statistically. Agent based modeling allows enormous flexibility in assumptions, and agents can be modeled at any level or even multiple levels of scale. Like other modeling methods, this technique has both advantages and important limitations. The agent-based model was accessed from COMSI's Net computational library and run using NetLogo. The model is used to simulate trades between buyers and sellers within different subhousing markets in the Detroit Tri County area in Michigan. The temporal scale of the model is 1 year. That is, one time step in the model represents 1 year. Every year, households make decisions to become buyers and to trade with sellers or banks. There are two components of the model: geospatial environment and agents. The geospatial environment provides a geographic boundary for the simulation area and submarkets while providing a physical environment for agents and households to be located. It includes the artificial housing market, which comprises three different submarkets: downtown, city suburban, and far suburban. There are two types of agents in this model: households and banks. For the purpose of simplification, one agent in the model represents 100 households. Household agents can further be categorized into two more types of goal-oriented agents: buyers and sellers. Buyers aim to find an affordable house by proposing a bid price to sellers. If buyers are not able to find affordable properties in 4 consecutive years, they are removed from the system, that is, they displace. Sellers aim to post an ask price and maximize their profits from the trades. Sellers who fail to sell their houses are forced to leave the system, that is, they are displaced. When this happens, the bank agent takes over the unsold houses and attempts to sell these houses. Banks inherit attributes from the sellers they take over. There are two steps involved in model initialization. The first is scalar parameter initialization. This includes initializing the demand-supply ratio, the half-bank flag, and the price drop rate. Generation of sellers and buyers is governed by the demand-supply ratio provided during the initialization of the model. When demand-supply ratio is 0.5, the number of buyers and the number of sellers in the housing market on the model at the time of initialization is equal. This indicates an equal demand and supply. When the demand supply ratio is set to less than 0.5, that is something like 0.1, it would reflect demand exceeding supply. There is more buyers than sellers. And when the demand supply ratio is set to something higher than 0.5, like 0.9, it would be the opposite. The half bank flag, if set to true, means that a bank agent is present in the model. Otherwise, there is no bank agent. The price drop rate is set to 10% by default and can be changed. This is the rate at which sellers reduce the price of their houses if they are not sold in a year. The next step is vector parameter initialization. The model is initialized based on socioeconomic and geospatial data of the study area. The socioeconomic data, example, income, employment status, house prices, comes from the decennial census for each census tract in the study area. For each census tract in the study area, 1% of the total number of households within the study area are represented in the model for simplicity. There are 3 stages of the initialization process: create households, assign employment status, and assign house price. The households are initialized by using the income background from the census dataset. For instance, if 500 households fall into the 10,000 to 15,000 income range for a certain tract, 5 household agents will be generated with their incomes assigned to this range. If the household is generated within the 10,000 to 15,000 income range, the variable H income for that agent would be set to 10 plus R, where R is a random number between 0 and 5. After the generation of households, several socioeconomic attributes are introduced to the household agents, like employment status and house prices, which provides the household agents with more heterogeneous attributes. Employment status is extracted directly from the census data to assign each household agent an employment status. If 20% of the households are employed in a particular census tract, the model assigns 20% of households in this tract as employed and the rest of them as unemployed. The procedure for assigning house price is similar to that of assigning employment status. We use the percentage of households falling into various house value ranges. If 20% of house values fall between 50,000 and 100,000 for those households, the variable H cost would be set to 50 plus R, where R is a random number between 0 and 50. On this slide, we can see the spatial distribution of employment rates and the number of households in each census tract. This is a list of the attributes associated with each agent in the model. At each time step in the model, all household prices are increased based on annual inflation rates. Regular households do an affordability check, where they check if their budget is less than the cost of maintaining the house. If the household is no longer affordable, the household enters the housing market as a seller. Seller households, if they are employed but are unable to sell their houses for over 4 consecutive years, there is 4 time steps, they may stay and keep trying to sell the household until a buyer is found. But sellers that are unemployed, if they cannot sell the house in 4 consecutive years, they will be removed from the system, akin to foreclosure. At that time, the bank agent may take over their houses and keep trying to sell it. The ask price decreases based on the price drop rate assigned in the next time step when the house is not sold. Buyers who fail to find a seller or bank to trade with increase their bid prices based on their budget. This concept is based on land market models. If buyers are unable to find a house to purchase in 4 consecutive years, they will be removed from the system. This dynamic indicates that those buyers who cannot afford a house in any of the submarkets based on their financial status may move out from our study area to somewhere else. One of the steps that happen in each time step is trading. This step comprises of 2 stages. Buyers find sellers and price negotiation. Buyers search for sellers by moving to different submarkets. It is assumed that a buyer's preferences based on security issues would be primarily for far suburban. If not far suburban, then city suburban, and the least priority would be given to downtown. Thus, buyers are allowed to enter the city suburban market only after searching the far suburban market and not finding a match. Similarly, they're not allowed to enter the downtown market until they search the city suburban market and don't find a match. The bid price is a function of income. To determine whether a buyer can afford a house in an area or not, buyers have knowledge of all ask prices of the area. The buyer's bid price on all seller houses would be bid price less than ask price less than 1.1 times bid price. So that is the if the ask price of a house is anywhere between the bid price and 10% above a household's bid price, it would be considered. Price negotiation, the price negotiation step is where the seller completes trade by selling to the maximum price bidder. In this section of my presentation, I share the results of my analysis on varying the 3 scalar parameters: the demand-supply ratio, the price decay rate, and the presence of a bank. When demand is much lesser than supply, the number of far suburban households decreases drastically. When demand is much greater than supply, the median price in the city suburban and far suburban areas is found to decrease. When there is a higher price decay rate, the number of households decreases faster but not significantly. A 0% price decay rate makes the downtown house prices increase and diverge from the city suburban prices towards the far suburban prices. When the price decay rate is 5%, prices increase in all 3 areas, while a constant gap is maintained between the city suburban and downtown household prices. A very high price decay rate, like 20%, drastically decreases the median household price trends in downtown and city suburban areas. The presence of a bank reduces the rate at which the households in the city suburban area decrease. Presence of a bank reduces median prices in all 3 sub-areas. It also maintains the difference between the far suburban and downtown area, which reduces significantly in the absence of a bank. Presence of a bank also sustains the median price of city suburban areas before they take a significant hit after around 5 years.